In my previous video, I did projectile motion, solving it with Hamiltonian mechanics. And I said, hey, wouldn't it be cool to do this in polar coordinates? So that is now. Now I'm going to do that. I'm going to do this in polar coordinates, and I don't even really know why, but it will be fun. You know, sometimes you just got to do things not because that's the best way to do it or you're going to find something out, maybe you will, but just because it's kind of fun. So let's just do this. Let's use two crazy things for something that you could just do with basic algebra, really. Projectile motion. Okay. So let's get started. Number one, the Hamiltonian. So the Hamiltonian, we can find the Hamiltonian as we have more than one variable here, right? We're going to have r and theta, and pr and p theta. So we're going to have two degrees of freedom. We had 2 degrees of freedom before. So we can find the Hamiltonian by taking, we're going to have pr, p theta, r dot, and theta dot. Those are my two variables. And then we're going to subtract the Lagrangian to get the Hamiltonian. Now, but the key thing here is, well, how do you find the momentum? So momentum we can find also from the Lagrangian. So we're going to have to write down the Lagrangian, the partial of L with respect to qi dot. So PR is the partial of L with respect to r dot. P theta is the partial of L with respect to theta dot. And you should do this, right? Because sometimes the momentum in your new coordinates aren't always so obvious. And then these are the Hamilton equations. And so we can find an expression for qi dot, which would be r dot and theta dot, and pi dot, which would be pr dot and theta dot. We're going to get 4 differential equations. And then we're going to solve it with Python. So should I add Python in here too? This is going to be everything. Everything, everywhere, Python all at once. Okay, let's get started. The first thing we need to do is to write down our Lagrangian. Now, I'm going to take one shortcut here. So the kinetic energy term and the potential we can write in Cartesian coordinates. It's always easiest to write in Cartesian coordinates. Then Cartesian coordinates, it's 1/2 m x dot squared plus y dot squared, and the potential is mgy. Okay, then I can find an expression for x and y in terms of theta and r and get these values. So let's say in polar coordinates, x is r cosine theta, y is r sine theta. So if I want to get x dot squared, I can take the derivative of this. So x dot is going to be the time derivative of this function. So that's going to be r dot, the derivative of r, times the cosine of theta, and then minus r theta dot sine theta, right? Because I have to take the derivative of cosine theta, which is negative sine theta, and then I have to take the derivative of theta, which is theta dot. So that's my x dot. Y dot is going to be equal to r dot sine theta plus r theta dot cosine theta, because the derivative of sine theta is cosine theta. Okay, so if I square this and add it to this, I'm going to just tell you, okay, because I'm not going to do this because it takes a lot of, I've done it like 80 billion times, but you should do this. I'm going to say do this. So do this x dot squared plus y dot squared. So first of all, I'm going to get an r dot squared cosine squared theta and an r dot squared sine squared theta, and the cosine squared plus sine squared is 1. So I'm going to get, this is r dot squared. And then I'm going to get this term, same thing's going to happen on r squared theta dot squared, r squared theta dot squared, sine squared plus cosine squared. So I get the plus r squared theta dot squared. Then there is a cross term. But see, I'm going to get this times this. I get r sine theta cosine theta, r dot theta dot. But then I'm going to get the opposite up here because I have a minus sign. I'm going to get 2 of them. And so they cancel. Okay, so the cross term cancels and that's it. And then mgy for the potential is pretty easy. So the Lagrangian is going to be 1/2 m r dot squared plus 1/2 m r squared theta dot squared minus mgy, which is r sine theta. That's pretty cool. Okay. Now, I want to write the Hamiltonian, but I need the momentum. So let's find the two momentums. PR is the momentum in the r direction. And that's going to be equal to the partial of L with respect to r. And so, no, r dot. There's a dot right there. So there's only one r dot here. It's right there. So if I take the partial of this with respect to r, I get 2 over 2 m r dot. So m r dot. So mass times velocity, which is fun. That's real momentum because r dot's a position coordinate, but that's important. Now what about p theta? P theta is going to be the partial of L with respect to theta dot. Now I'm looking over here, there's the theta dot, okay? So I get 2, bring the 2 down, I get 2 over 2, and I get m r squared theta dot. So in this case, the theta momentum is not just mass times velocity, right? We have this mr squared term in there. It's not real momentum. I mean, it's angular momentum. Spoiler alert, that's angular momentum. Okay, so next, what can I do? Now I have p theta and r theta. I can write down the Hamiltonian. I'm going to write it down as in a non-standard form, and then we'll fix it. Okay, so Hamiltonian H is going to be equal to, you can't see that. It's p theta. Let's just write this as a pr r dot plus p theta theta dot minus L, which is minus 1/2 m r dot squared minus 1/2 m r squared theta dot squared plus mgr cosine theta. Now, and then you put over here pr is m r dot, p theta is m r squared theta dot. So I want my Hamiltonian in terms of position and momentum. I want r, and I want theta, and I want pr, and I want p theta. That's it. So I don't want to have any r dots. I don't want to see any r dots in there. I don't want to see any theta dots. So there's another one. I need to get rid of these. Yeah, right there. Okay. So over here I can say r dot is pr over m, and theta dot is p theta over mr squared. If I now make that substitution, I get H equals, I get PR times PR over M. So I get PR squared over M. This is going to be plus P theta squared over MR squared minus 1/2 M R dot squared is P squared over M squared. PR squared over M squared, and that's going to cancel. And then I get minus 1/2 M R dot squared is going to be PR squared over M squared R P, and there's an R. No, that's P. I'm sorry, I did that one twice. I'm right here. So minus 1/2 M R squared theta dot squared is going to be P theta squared over M squared R to the 4th. And then I still have this other term over here, plus mg r cosine theta. Poor planning on my part. So these cancel with 2, cancel. So I get this, pr squared over m minus pr squared over 2m. So I can combine those two together, and I get H equals pr squared over 2m. That is the kinetic energy, p squared over 2m. And then the other term, I'm going to get plus p theta squared over 2mr squared, right? Combining these two terms, I get, there's the same thing, but that's a negative 1/2. And then I have plus mgr cosine theta, and that's my Hamiltonian. But you'll notice there's no theta dots in there, there's no r dots in there. It's all in terms of p and r, and pr and r, p theta and theta. We're ready to rock and roll. Whew. Okay, so let's apply the Hamilton equations, which I wrote right here. So I'm going to get 4 of them. Let's do r first. So I'm going to say r dot is the partial of ph. Oops. Come back into focus. Well, I want to do that. Let's see if I just switch to the computer and then switch back. Let's see. What the heck? It's making me mad. I don't want to stop. I thought I was making great progress. How long has it been out of focus? There we go. I'm sorry. Okay. I'll just try not to move my hands. Keep your hands down real low. It was moving the paper. That's what did it. I bet there's like dirt. Look at that. That's weird. Okay, there. What the heck? I think I must have a filter on. Video effects off. Huh. I don't want to redo this video. Okay, don't. Just behave. Just behave, please. I'm asking you. Okay. So I have r dot is the partial of h with respect to PR. I'm scared now. I'm scared of focus problems. And PR dot is negative the partial of h with respect to r. So let's write these two differential equations. So r dot is going to be equal to the partial of this with respect to PR. So I only have one PR here. And so I just bring down the 2 and I get PR over m, which, spoiler alert, we already knew that, right? We already said that up here. And then PR dot is going to be the partial of this respect to r. Well, I do have two r terms in here, right? So I have to take the partial of this respect to r. So I'm going to get, there's a negative sign, right? I have a negative sign. But this, when I take r to the negative 2, I'm going to get another negative sign. So I'm going to get p theta squared over m r cubed, because that's going to, I'm going to decrease that by, you're kidding me. Come back on. There we go. No? It's like focus not over here. Okay, I'm going to do something I don't normally do. I'm going to stop this and then fix my camera and then edit. Okay, let's see if that fixed it. So I apologize. And so now I have, I took the partial of the Hamiltonian with respect to r, and I got that first term. And then I have this other term. Now remember, there's a minus sign in the partial right there. So I'm going to get minus mgr cosine theta. Minus mg, that's not cosine. It should be sine. Sine. I think I was having focus problems early on. And so if you're like, hey, this guy's crazy and he's doing crazy stuff, I understand. mg sine theta. That's that. Okay, so now I have r dot and pr dot. So I have two differential equations for r. Now let's do the same thing for theta. So theta dot is going to be the partial of h with respect to p theta. So p theta is right there. So I take the partial and I just get p theta over m r squared. And then I get, my hand's like really low. I'm paranoid now. I can get p theta dot. It's negative the partial of h with respect to theta. And there's only one theta term in there, and it's right here. So if I take the partial of that, I get mgr cosine theta. Okay. So there. I have four differential equations. So I'm going to solve this by saying, number one, I can calculate PR dot, and I can use that to update PR. So I can say PR2 is PR1 plus PR dot delta t. And then I can calculate, I can use that to calculate theta dot, p theta dot. No, I can use that to calculate r dot. Yeah, r dot. Right there. And then I'm going to update r. R equals R2 is R1 plus R dot delta t. And then I can do the exact same thing for p theta. So I've done this before, so let's do this. We've got a lot of coding to do because we've got a lot of graphs to make. So let's just jump into it. I do need initial conditions, and I tried this out, and I remembered that there is a trick. The trick is I can't have. I'll show you. Okay, I'm just gonna let's go ahead and make this program. So I'm gonna calculate. I need these equations right here. I'm gonna model these numerically in Python. It's gonna be fun. I'm gonna make 3 graphs. Okay, here we are. And this one won't lose focus because it's a computer, right? So that's better. So let's just go ahead. I'm going to go ahead and make, just to make one graph. F1 equals G curve. And I don't really care because I want to test to make sure that everything's working. So I need a mass. Mass equals 0. I need G. Make that a little bit bigger. I need R. I would normally start, what's my initial conditions for R and theta? And then P, R, and P theta. I mean, R is easy. I want to start at the origin. And then theta is undefined, right? And then P, R, and P theta, it's kind of difficult to find. So I'm just going to pick values, and then we could find the X and Y velocity from that. It's easier to go that way. I know. Okay, so let's just put R is equal to 0, and I'll show you what the problem is. Now I'm going to say theta is equal to pi over, let's say 45 times pi divided by 180. Yes, that's pi over 4. And then I'm going to say PR, the momentum in the R direction is 1. I'm just picking a value. P theta is 0. I'm just picking the angular momentum is 0. It doesn't matter. You can pick whatever you want. But I need to have those values to update them. I can't update what I don't have. Now t equals 0, dt equals 0, and let's make a loop, not 0. That out of focus thing really just threw me off. Sometimes you get some mistake and it just throws you off. Let's just run this for a second in real time. And the first thing I want to do is to calculate PR dot. So PR dot, and I'm looking at my equation over here. It's just going to be P theta, which I know is 0, squared, divided by M times R cubed. I have all those values, so I can calculate that. And then I have minus M times G times sine theta. Now you see right here the problem. Can you see the problem? If I start off with R equals 0, that's cool, but right here I'm going to get P theta squared divided by MR and R is 0, so I'm going to get an infinite thing. So I can't have R equals 0. So I'm just going to put 0.1. Let's just put it at 0.1. Who cares? Okay, so now that I have PR dot, I can update PR. So PR is PR plus PR dot times dt. That's just your standard numerical calculation. Now, let's go ahead and do the theta stuff. Let's do all the dot, the momentum stuff first. So let's update the momentum. So P theta dot, again, I have this equation. I'm looking over here. P theta dot is M times G times R times cosine theta. And then I can use that to update P theta. P theta equals P theta, nope, plus P theta dot times dt. Now I can update R and theta. So I'm going to first calculate R dot. So now I can say R dot is equal to, again, I'm looking at my equation over here. It's just PR over M. So PR over M. I just calculated PR, so I know that. And then I'm going to update R. R equals R plus R dot times dt. Now I'm going to do the same thing for theta dot. Theta dot is, looking at my equation, theta dot is P theta divided by M times R squared. So theta equals theta plus theta dot times dt. That's it. And then t equals t plus dt. Now let's plot. Let's just plot just for fun right now. R versus theta. I didn't put any labels or anything. So f1 dot plot R theta. Let's just see if it's working. Let's just see if we get something, because we might not. See? Okay, so something happened. Let's just, it ran. It just didn't plot anything. Let's just print R theta PR, P theta. Let's just see what happens if I print all those things. Is it giving me values, or is it giving me stuff that I don't know? Yeah, see, that's what happened. I got an unknown value. Okay, so I made a mistake somewhere. Okay, let me just look. MGR. Oh, M is 0. You can't have 0. There. Okay, so this is a polar trajectory, right? R versus theta. But it seems to be working, but I don't know if that's what it should look like. So let's plot X versus Y. Let's switch back to Cartesian coordinates. I know what the trajectory should look like there. So let's calculate X. X equals R times cosine theta. Y equals R times sine theta. And then let's plot X versus Y. I don't need to print this because I found my mistake. Projectile. Oh, what did that do? That looks like a projectile. Did I do Y versus X? X versus Y. Why is it backwards? Huh. This is plotting X on the... X equals R cosine theta, Y equals R sine theta. Plot X versus Y. What did I do wrong? G, just checking. At least I don't have focus problems. G, okay, I'm gonna jump. I did practice this and I got it to work, and so I'm just gonna copy my other code. I know that's cheating, but I like to make sure things work, and I posted this in another window, so I'm gonna copy this. Let's see if I just come over here, just delete everything. It's the same thing. So what do I have up here? I have a bunch of, I have 3 graphs. I'm going to show you those in a second. So I have M, G, R, theta, PR, P theta. I have the same thing. PR dot, I'm just looking, M, R squared, MG, sine theta. That's the same. P, oh, that's, of course, it's the same. Okay, that's fine. There's R. Let's plot this one as X versus Y, and let's just see if this one works. And that one's working. I don't know what there's some dumb error, but there's my parabola. That's my trajectory. Okay, so let's go and fix this up, because now what I have one trajectory. I want to plot R versus theta, so that's going to put this back at. Don't want R in the horizontal. Let's do R versus theta. That's my trajectory in polar coordinates. And then I'm going to plot a phase-space plot for R and PR, and then a phase-space plot for P theta and theta. So I have two phase-space plots. And let's go up here and make these look nice. So I have a graph. The first graph is skinny and long. Let's put a title. Let's make everything look nice. And the title is going to be polar trajectory. That looks nice. X title equals R, Y title equals theta. Okay, so in Python, Web VPython, if you make a graph and then put a function right below it, that function is going to be in that graph. So you don't have to explicitly say it. Now I'm going to make another graph right here, and it's 200 by 200, and that one's going to be my my R graph, my R phase space. So let's put title equals R phase space, and then X title is going to be equal to R, Y title is PR, and then down here this GT, that's for theta. Let's put title equals theta phase space, and then X title equals theta, Y title equals P theta. Okay. And then everything should be true. And then let's run it. Okay. So there's my trajectory in polar coordinates trajectory, right? And then I have two phase-space diagrams, one for theta and one for R. And so I like the dots in there too. So you can see this one, the R is decreasing when the R momentum's increasing. It goes up here, which makes sense, right? because, well, it doesn't really make sense because it's hard to think about projectile motion in polar coordinates. And then theta goes up here, it has some value, and then it's decreasing. Because, imagine I'm launching the ball this way. As it moves on, theta is going to decrease, right? Because if you're looking at plotting where that thing is as a function of time, it's going to decrease. So I think that's okay. And there you go. The end. Okay, now I got to combine those two videos together, and that makes me mad, not happy, but that was kind of fun. I had fun. Do you want the code for this? Yes, you do. I'll give you the code.